Final sessions entitled Compound Representations. Please be seated. Compound representations. I'm not sure what that means, and hopefully we'll find out by the next two speakers. First will be Andre Fenton, and later will be Jim Knierim. So Andre?
So this is, truly an honor to, be here to honor Jim, and I'd like to thank the organizers, which includes me. One of the real reasons for doing this is, in many ways, as we've heard today, that Jim has influenced many of our scientific careers, many of our lives, and I'll try in presenting sort of forward-looking and substantially new data, sort of show you the threads of Jim's influence throughout my career. I figured, this symposium has in the title sense of direction and their head direction cells, but we haven't really seen a movie of a head direction cell, as Jim liked to present them. So here is a head direction cell, if you can hear. And what's impressive about this, for those of you who've never actually seen a video of a head direction cell, you're listening to the action potentials, right? It's really unambiguous. So this is a movie I made in the lab as a graduate student, and I figured out which rat it is even. It's rat R97. And I'm certain that Jim actually, watched part of this recording. So that's the thing I'm going to focus on. I'll introduce a little bit about place cells. First, at some point, Jim was actually written up in the discovery of head direction cells was written up in the New York Times. In fact, it was inspired by one of the publications of John, interestingly. They had done a study looking at the development of spatial tuning in the entorhinal cortex and hippocampus, and one of the first cells that became fully formed, if you will, just as an animal walks out of its nest, was the directional cells, directionally tuned cells. And so a New York Times reporter came and talked to Jim, and Jim loves this picture in particular because if you look, he's interviewing some strangers about the direction of something. I can't remember what it is, if they were supposed to point to north or something like that, but they were supposed to point to north, and one of the lovely things is that they're apparently confused. And I'm going to show something not unlike that in these cells in a few minutes. So one of the things that I want to really sort of stress, you've sort of heard it, there was a real sense of family and community in the Brooklyn lab. And as Jim liked to say, and often likes to say, we really did have a very good time. So one of the first things I did when I got to the lab was I learned to record place cells. And I have to say, I was very bothered by actually watching those cells and listening to their action potentials, in particular because in many of the pictures you've seen, we have these beautiful firing fields here from the time-averaged activity, and one would expect, if this was useful for getting around in space, that whenever the animal walked across that firing field, you would expect the cell to fire. We don't expect everything in biology to be absolutely precise, but you'd expect them to fire more or less reliably, at least in time. And I could never see that. And so one of the interesting things is, Bob Muller, who was my mentor, had a very strong personality and had very definite ideas about place cells and how crucial they were for navigation and the cognitive map. And I remember arguing with Bob, and he'd say, "You're a punk, you don't know what you're talking about. I've looked at thousands of these things." And it was only really after pointing out to Jim that, this seemed really bothersome to me, Jim, that, these cells don't fire reliably where I would expect them to. And he said, "Well, why don't you try and prove it?" And so that's one of the things that we embarked on, trying to actually quantify how unusual that variability was. And as with many things, Jim had a book in his office. It was by Cox on point processes. And so that's where I started to learn about how to actually characterize the discharge of these cells. One of the ideas was that these cells, it came to pass that the cells don't actually discharge in a way that you'd expect for a random point process. That's not going to be the story today, but one of the early thoughts I had, and you'll see where that comes from in the next slide, was that very possibly the hippocampus and these cells were not simply responding to place, but to responding to something like a place from a particular point of view or spatial reference frame. And so that's something I'm going to spend the rest of the talk describing. And so as I've ended up developing, we decided to study how spatially tuned cells, discharge during navigation, in particular in at least two spatial frames. And one of the tasks that we developed, I call it the two-frame place avoidance task that will frame this talk, sort of looks like this. Here's a rat who knows how to do this task. The red space is anchored in the room. It's colored red, not for the rat, but so that we can identify it. And the blue space is rotating with the arena, so the computer is able to track where the animal is with regard to a particular part of the room, as well as where the animal is with regard to a particular part of the floor, and the rat's very capable of avoiding these two places, if you will, that are definable simultaneously within two spatial frames. And if you look over there on the right, that's the track of the animal during about 15 minutes or so. You'll notice that whenever he was in the room frame shock zone, that's the red dots are showing where he got shocked. The shocks were actually dispersed on the arena surface. And if you look at where he was when he got shocked for being in the particular rotating part of the floor, those shocks are dispersed in the room. And rats learn to do this task very quickly. I'll show you a learning curve in a minute. And the hippocampus is necessary for doing this task whenever we've checked months after training and such. And so one of the early studies that we did in this task looked at hippocampal activity, place cell activity in particular, as animals solve this task. And one of the things that I remember Bob Muller being particularly impressed by was that it wouldn't be possible to expect to find these cells that discharge with respect to the floor. And he was very happy that it took us a long time to actually find examples of those cells. And I'm going to show you here, one of those examples. It's this cell here. And so if you look here, as the arena is rotating in different orientations, in particular, just let's focus on here, there's a nice firing field, but it's defined in the rotating coordinate system. And this is a more properly behaved place cell that was anchored to the distal cues in the room. But these are very, very rare. We've seen about 4 or so of these cells in approximately 1,000 or so. What they tend to do instead is alternate their activity, sometimes discharging for being in a particular part of the room, sometimes discharging for being in a particular part of the floor, and you can sort of see that here if you do the right kinds of things. So there are several ways to do this. We developed an information measure that's shown here, and what's plotted here on the y-axis in red here is the amount of information that the cell discharged in about 130 milliseconds, the amount of information about where the animal was in the room, in blue, the amount of information about where the animal was in the arena, and the red is the discharge of the particular cell during that 133 milliseconds across a long recording. And so you can see this rare cell, when it discharges, it seems to reliably say something about where the animal is in the room. In this case, The other cell, one of the rare ones, also, when it discharges, says something about where the animal is in the arena. But these are extremely rare. And when you take a collection of these cells, this is sort of the pattern that you see. There are moments of time when the ensemble discharges reliably for where the animal is in the room, and that in red here, and other times it discharges reliably for where the animal happens to be in the arena, and this toggles back and forth in hippocampal activity. And there are a bunch of interesting things that we won't dwell on here, but you can notice there's more red here in this recording and more blue here, so this ensemble seemed to have a preference for signaling information in the room, whereas in this case it had a preference for signaling information in the rotating frame. And if you look, I'll just skip this, if you look carefully at the behavior, you can see actually the switching back and forth is actually purposeful. If we plot here how far the animal is from the room shock zone in red and how far he is from the arena shock zone in blue, shown here, and we can look at it as a difference over here. And we can see that as the animal is closer to a particular shock zone, the hippocampus seems to represent information in the corresponding frame. So as he's closer to being near the room shock zone, activity here is room preferring. As he's closer to being near the arena shock zone, the rotating one, hippocampal activity preferentially represents being in the arena. And you can see that in some detail here as he approaches one shock zone. For example, he was in the arena frame. It switched for a moment to the room frame. It went back and forth and settled into the arena frame, and so on. So since this is about Jim and head direction cells, what I decided to do is to show you an experiment that we're just completing the write-up for. And Hay Park, who's in the room, spent a number of years collecting data here in the medial entorhinal cortex and hippocampus, and we're going to focus only on the directionally tuned cells in the medial entorhinal cortex for this. So given the title of the symposium, The Sense of Direction and the Cognitive Map, what might we have expected these cells to do if they're contributing or crucial to the cognitive map as we've talked about? Well, there are a number of things number of questions one might want to ask. Which spatial frame will the cells preferentially discharge? So which frame will organize the head direction cells, the distal frame or the rotating local frame? You've heard information and opinions about the cells being preferentially tied, for example, to distal cues. But the animal in this case is also needing to use these rotating local cues to know where it happens to be. So how will that play out? So will the discharge relationships amongst the head direction cells actually maintain during this recording, as you might expect for something that's part of a ring attractor? Or will it dissociate into two ring attractors, if that's a possibility, given that the animal needs to know about where it is and presumably directions in the two spatial frames? What would you expect? Will the directional discharge, will it follow the behavior of the animal? As I showed you, the place cells follow the behavior of the animal depending on its local needs during the task. So we'll be able to provide some answers to that. So the first thing is, here's what the learning curve looks like. When Hay trained these animals, it's a little bit different than what we typically did because we wanted to record cells in the medial entorhinal cortex. We had a somewhat larger arena. The arena is 1.2 meters in diameter. And you can see here that this is the trial structure. Each session was 30 minutes long. It would be stable. Then we'd rotate it for 30 minutes. Then we'd stop the rotation again. And here's what the learning looks like when the arena is stable and when the arena is rotating. And Hayes only started the recordings after the animals were very competent at the task. And as I said, she recorded place cells in this somewhat larger arena. This is what the arena looked like. Here's an example of a CA1 place cell when the arena is not rotating, a grid cell, and a head direction cell. And we're going to focus on the directionally tuned cells. So this is what we saw. Here is an example of, what is it, looks like 6 head direction cells. When the arena was stable, they all look directionally tuned, right? Those polar plots. The further away from the origin, the higher the activity. But we were very surprised, and in fact, Unhei was not just surprised, but very distraught actually, that when the arena was rotating and you plotted those directional tuning curves, the directionality seemed to have, strongly degraded. In this case, it looks particularly bad. And she didn't lose the cells, but when she stopped the rotation, directionality returned. It didn't actually return to exactly the same orientation as it had when the arena was stable for the first time, but the directionality returned. And you can quantify all this. Not surprisingly, the LFP power and stuff that you would expect for ongoing activity looks more or less similar. The firing rates of the cells maintained during the rotation, just as it did before and after the rotation. But the directionality was degraded. Here you can plot the directionality in at least 2 different spatial frames, either the room frame or the arena frame, the rotating frame. It looks bad. That you can ask about the directional stability in one way or another, or what happened to the direction preference, how it might have changed. So it's not that the direction signal went away completely, but it became surprisingly degraded. So that was a little disturbing. So what we thought we would do is try the same sorts of decoding tricks that you heard from an earlier talk. And what's shown here is we can use a maximum likelihood decoding and try and predict which direction the animal's head is actually pointing in from an ensemble recording. And that certainly seems to work very well. What's shown here is the animal's actual head direction in blue as it fluctuates during the stationary session, and in gray, the decoded directions, they mostly track pretty reasonably. And what's shown here in the color plots is really just some, for example, ensembles. What's plotted on each axis is the error, and you can actually use the priors, or you use the tuning curves, the directional tuning curves from the first stationary session to make the predictions about where the activity would be, which direction the animal would be pointing, or the ensemble would be pointing in the second stationary session. And because these points are close to the origin, you can see that means things are reasonable. However, you'll notice in these 2 ensembles, as I pointed out, the directionality seems to have shifted a little bit in the second stationary session, and so the points are further away from the origin there. But that's what we saw during the stationary session. If you look during the rotating session, this is what you get. What's shown in blue is the animal's actual head direction in either the rotating frame in blue or in the room frame, the stationary frame in red, and the decoding, which is optimal here for whichever frame gives you the weakest error. And what this shows is that it's very hard to decode from this activity, any prior that we choose. We can't decode very well or for very long. You can also look here, I showed you this kind of analysis for the place cells. We can measure how close is the animal to one shock zone or another. If you remember, in the hippocampus case, if the animal was close to, say, the red shock zone or the stationary shock zone, then activity tended to be better organized in place cells according to the room or corresponding reference frame. And what we see here is not a very strong correspondence, but certainly a correspondence. And the correspondence here is shown for a particular recording. Oh, let's bring that back. Here's about 3 minutes of recording where you can see the difference in the change of preferential information being in the room or arena, fluctuating here in green, with the distance to the ratio of the two shock zones. And they tend to be anti-correlated. They are always, for all the ensembles we look at, here's the examples for the 4 I showed you, they tend to be anti-correlated. So if the animal's close, let's say, to the stationary shock zone activity, the head direction activity tends to be oriented or better organized in the opposite rotating frame. So that's what we saw. So at this point, I'll sort of pause, and I talked to Jim about these data as we're writing up the paper. I think on Wednesday, he denies remembering saying this, but I actually I'm pretty convinced he said this. He said, "But John O'Keefe is not going to like this." But then we decided to, and I think actually John will, because we'll come to I think a more an interesting conclusion. So since every talk, all the last 4 talks I believe have quoted this phrasing from Jim's 1973 paper, I thought I would do so too, and I highlighted something that helped us make sense of what I just showed you, which frankly doesn't make a whole lot of sense, but it's what we can see. So to quote, "It may not be possible to find a behavioral correlate of a neuron, right? For its firing may signal something not directly related to overt behavior, right? Such as a drive state or some idea the rat has." And so we're going to pursue that idea for a moment. And John Kuby, I think, showed this other figure from the 1990, the second 1990 paper. And that's a very important figure, because what it shows is that the relationship between a pair of head direction cells seems fixed or constant across environments, and invariant. And so we decided to take advantage of that and look at the relationship amongst the cells in our ensembles. And instead of trying to project and understand the activity in terms of the external space, our overhead camera, we decided to try and understand their activity with respect to some internal notion, the kind of thing that Jim might have said the rat has in mind. So how did we do that? We did pretty much what you saw Adrian describe. I've shown here 3 example spike trains, and we could compute the correlation between any pair of spike trains, and we can ask on any piece of recording, what's that relationship like for all the cell pairs? And then we can ask, given that you know the relationship for a cell pair in one recording, what's that relationship like in the second recording? For example, the first stationary recording with the second stationary recording. And here's some examples. Here's a pair of cells that have similarly tuned directional profiles in the first stable session as well as the second stable session, and they're shown here. They have a positive correlation that seems to be more or less preserved. Here's another cell pair. They tend to have opposite tuning, if you will, directional tuning, and their correlation in the first stable session compared to the second stable session is pretty close to the diagonal one, so it's stable, and it happens to be negative. So you can see that of all the cell pairs, there are positively correlated cell pairs and negatively correlated cell pairs, and as described before and expected, they're relatively stable. In fact, they're very stable. It's a quite high correlation at whatever time scales we've looked at here, in particular within a 40 millisecond time scale. That's the time scale of the correlation, or out to a second. So what happens when you do the same exercise for comparing the pairs of cells during the rotation? And what's remarkable is it looks exactly the same. You'll notice that the correlation here is very, very strong. If you know the relative timing or the relative correlation of a pair of cells in the stationary session, you have very, very high likelihood of knowing it during the rotation. despite the cells not showing you very well organized directional tuning from the external point of view. It's just another way of showing the same data. So we decided then to actually look to see if we could recover what the directional signal actually was. And this should make John happier. And so how did we do that? Well, we decided that we could take each cell's discharge and pretend that one of those cells was the reference frame, if you will, for the activity of the other cell, just more or less like the tuning curves that we saw in the 1990 paper. But we're going to do this now in time. And so what we decided to do is to take a spike, let's say from cell 1, this spike here as the reference and when that cell fired, we knew what the animal's head direction was. And then we could look at the temporal offsets. We did this out to about 5 seconds and measure the change in head direction measured by our camera for those other spikes of the second cell. And when you do that, you can actually get a very nice directional signal. Here it is. This is the directional tuning from the external point of view, and here's the directional tuning from this internally registered or internally organized reference frame, if you will. And so when you now look at the data during the rotation, this is what you see, right? So while the directional tuning in this instance looks rather well preserved in the arena frame, it looks poorly organized, but not null in the room frame. And obviously, when we stop the arena rotation, this internally registered directionality came back. So we can sort of quantify this. You can see that this internally referenced directionality is maintained. The errors and so on are no more than you would have expected. And so here's an instance, if you will, of these cells maintaining a very strong and very clear sense of direction. It's, however, not well described or accurately described on the time average using an external point of view or an external reference frame. It may seem that the animals have some ability to pick and choose how they'd like to register this system. How they'd like to register their internal sense of direction within the external frame. And in many ways, as I'll wrap this up now, to summarize, you can't see that. The spatial firing of what I hope to have shown you, at least of medial entorhinal cortical directional cells and other MEC cells that we've looked at, it seems poorly correlated with the azimuth and, in fact, with space during these rotating conditions, right? But it seems to be very, very well organized. In fact, you couldn't detect that we had done anything unusual if you looked at an internal spatial frame and looked at the correlated activity amongst the cells. The discharge pattern certainly has the flavors and some of the expectations you would have predicted for an attractor system, and those dynamics are very strong. And it would seem that this system, at least the activity that we've looked at in the entorhinal cortex, really seems to have a pretty good internal model of space. And rather than this system seeming to reflect like a mirror might the external space, it's almost the other way around. This internal model is being somehow projected into some interaction of it being projected and interacting with what is actually in the world to give the animal what appears to be its useful ability for knowing where it is. Its head might be pointing, and also, I would argue, where it happens to be. And maybe if there's nothing to remember here, the thing to keep in mind is that, one of the challenges is when and how much should we average. If we had looked at these data just in the long time scale average, looking for the overall tuning curves, we'd go away fairly confused, but trying to find ways to understand the activity on the short time scales reveals to us that there are interesting dynamics that we actually can use to make sense of the system. And just in a closing, we really did have a very good time. Okay?